Welcome everyone to this EuroPractice webinar. My name is Maria Martinez Balado. I'm a program manager at IMEC and EuroPractice, and I will be your host during the session of today. Today, we continue with the Compound Semiconductor webinar series that we started already last year. The first episode, as usual in this series, was an introduction to compound semiconductor materials, applications, and a market overview. This was given by IMEC. And then we had different episodes, each one dedicated to a single compound semiconductor material. This way, in the past weeks, we had webinars dedicated, for instance, to 4H silicon carbide CMOS technologies for harsh environments. This was given by Fraunhofer IISB. There was another episode on gallium arsenide technologies for power, low noise RF amplification. This was given by UMS. And last week, we had a webinar dedicated to gallium nitride technologies for power, LED, and RF applications given by IMEC. The recordings of these webinars and all the episodes that we have done in EuroPractice are already in our YouTube channel. So I invite all of you to go there after this session and watch your favorite episodes or discover new topics. Next week, we will conclude this series with a webinar on silicon germanium by CMOS technologies given by IHP. And today, the focus is all about indium phosphide photonic integrated circuits, and we will have the special viewpoint from the JePPIX ecosystem and a special focus on the use of indium phosphide PICs for sensing applications. To guide us through all this, we have here on this virtual stage our speaker of today, Dr. Víctor Dolores Calzadilla. And before he starts with his presentation, let me briefly to introduce him to all of you. So Victor received his Bachelor Engineering in Telecommunications from the National Autonomous University of Mexico and his Master's in Photonics from the University of Jena in Germany. In 2016, he got his PhD from the Eindhoven University in the Netherlands, and then he moved to Berlin and joined the Fraunhofer Heinrich Hertz Institute as a scientist of the Department of Photonic Components. 2 years later, in 2018, he went back to the Netherlands, where he has a hybrid role. On the one hand, he's an assistant professor at TU Eindhoven, and on the other, he's a program manager at the Photonic Integration Technology Center. Victor has a strong expertise in 3-5 photonic integrated circuit technologies, both on generic and membrane-based platforms, and he's currently engaged with PIC-based sensing research and technology development in cooperation with several industrial partners. Moreover, because this was not enough for him, he often participates as a lecturer in the JePPIX trainings. So with this, I conclude my part, and now it's time for you to enjoy Victor's presentation. I wish you all a very nice webinar, and Victor, when you want, the floor is yours.
Good. Thank you for the introduction, Maria, and thank you to EuroPractice for the invitation for this webinar. I will get started. I'm Victor Calzadilla from TU Eindhoven. That's my main affiliation, as Maria mentioned. And I will introduce today indium phosphide PICs for sensing applications, a little bit from the perspective of the JePPIX ecosystem. This is the outline of my presentation. So first half, I will talk about the JePPIX ecosystem, what partners are there, how we are collaborating, what kind of activities do we do, and the JePPIX offer by the different partners. Then I will talk in the second half about sensing applications, starting with integrated lasers because they are often at the core of different applications. And then I will briefly talk about gas sensing, fiber grating sensors, and also LiDAR sensing. The JePPIX ecosystem is basically consists of many partners with different role in it. So from foundries to design houses to basically companies doing software, producing PDKs, doing testing, packaging, etc. And basically we are collaborating to advance the state-of-the-art PIC technologies, and more importantly to support businesses, more especially SMEs, but also sometimes large-scale companies, to make their PIC-based products. Some of the activities that are happening usually in JePPIX is the open access technology. So this is through process design kits that designers can use to submit their own PIC designs to foundries and get them manufactured. Also, we do technology acceleration, and with that, I mean that we actually develop net technology, net manufacturing technologies. Also, we develop sometimes building blocks, and we collaborate in R&D projects. Most of the activities in JePPIX is about indium phosphide, but there are also some in silicon nitride, and now more recently becoming also hybrid. There are activities in the hybrid part, and the ecosystem development. We are active on road mapping, so in collaboration with industry partners, we gather every now and then to discuss the status of the technology and how to move forward. And training events and technology forums. So we provide also different formats of trainings for for academics, for industry, and so on. We participate in roadmaps. So every few years we make available online a JePPIX roadmap, and this is the current one, and you can find it in our website of the JePPIX. And we also collaborate several of the partners from JePPIX in the IPSR International. That's a collaboration between InP Photonics Academy and Photon Delta, where it's more, the global perspective. So trying to see, where this technology is going and what are the needs from the different users on a more global scale. Applications based on PICs are diverse, as some of you might know. And they are especially fine application where we need some low cost, small size, low weight, power efficiency as well, when we need to customize some light sources for a certain type of performance. And also more future oriented. Also, we are doing basically this technology is increasing more and more the integration density of the components on the chip, and with that you can address new markets, like for example computation. All of that is happening in the indium phosphide PICs ecosystem, and is enabling new applications. That's possible because with indium phosphide monolithic integration, it is possible to integrate different type of layer stacks into the same wafer, and that is from the physics perspective, but that makes it possible that in the same chip you can have lasers, efficient modulators, amplifiers, detectors, and a diversity of passive components like combiners, multiplexers, hybrids, polarization rotators, and so on. So all these building blocks are available in the library of components and can be used to design any type of complex circuit. And that is basically at the heart of the indium phosphide PIC technologies. How does the journey for a designer or a PIC developer looks like is what is represented in this slide. So JePPIX is always open to hear from different needs, different ideas from users, and to discuss whether that is feasible or not in this kind of technology. When that is yes, it is feasible, then you can do the PIC design in your lab, in your own company, for example. You can take out the specific multi-project wafer runs from foundry partners. Your chip can get fabricated. Then later they can go to testing or to packaging, and you can reach a prototype. So all this is open access, and you get support from JePPIX on whom to contact for what specific step, and what are the options, because there is not only one option to fabricate, there's not only one option to do testing, to packaging, to do the design. There are several options, and you can get some guidance from JePPIX. The offer of the partners is basically explaining this in this slide in a nutshell. So you can be guided to tape out for your design, but also if you want a pilot trajectory, a pilot manufacturing, you can also be supported. All the designs are based on PDKs and rely on a mature and scalable fabrication process, which is, we call it generic. And that means that with a single type of technology, a single type of library, you can address different types of architectures, applications. And more recently, we are more and more putting effort into test and measurements and packaging of chips that can be done more automated. The integration platforms we work with are here. So in the silicon nitride, will be consisting of Lionics International and Lion-Tech, which have very low loss passive components and others. And for the indium phosphide will be Fraunhofer Heinrich Hertz Institute, Smart Photonics, and 35 Labs, who are developing a platform at the moment. And HHI and Smart have a diversity of components in their library. Some of them are explained here. The important part is that, again, you can integrate lasers, amplifiers, detectors, modulators, and more. All this is made available through these PDKs, which is in the end basically integrated in a design environment. Here you find some of the partners we collaborate with, and they offer PDKs for different foundries. And what you can find there is basically the last status, the last information available, made available from the fab on the performance and tolerance of the different components. Also, when possible, we make intellectual property IP blocks available, and we try to, let's say, avoid reinventing the wheel. So that if someone needs a specific type of coupler, a specific type of filter, and someone else has done it already as a building block, either in a design house or we in a technical university of Eindhoven, we have a lot of different projects where we explore new components, new building blocks. If they are done, we try to make them available as an extension to the PDK of the foundry. And well, basically anyone can have access to them with specific conditions. Of course, but this really helps to accelerate the design manufacturing cycle, since you will be already basically starting from a specific known point and not just starting from scratch if you want to make a new type of building block. Manufacturing, once it is designed, of course, it goes to a manufacturing a foundry company, and they all are working on making the technology more reproducible, improve the performance of the building block, also increase the performance could be from speed point of view, for example, efficiency point of view, and so on. More recently, as I mentioned, we are spending more efforts on the testing. So colleagues here at the university, in the PITC, but also in other companies and partners, are developing methodologies, are developing software, hardware, to be able to measure the photonic chips in an automated way, so that in the near future, the designer can specify not only what design should be fabricated, but what he or she wants to get measured from the chip when the chip goes to the user, so that this can be measured even outside of your own lab. There are effort templates for assembly and packaging. So there are some certain rules how you can make your assembly and packaging easier or possible at all. If you make something very weird, sometimes it's not possible at all to package. And there are templates available for this, and you can find them in the PDK. And also, again, as I said, the last years, there is this trend to make a hybrid combinations of PICs, so that you can combine these two different types of platforms of chips. And of course, things become a little bit more complex. So it's good to really stick to the templates and that were generated in the last year from different initiatives. It's possible to combine two different types of chips. Here is an example of a lower line with laser, which was possible by combining a Lionics silicon nitride chip, low loss, with a Fraunhofer Heinrich Hertz Institute chip. And these kind of things are possible if your application needs basically certain performance that is only possible when combining two different chips. And that is the first half of the talk. Now I will get started with the second part, which is more about specific examples and applications on the sensing part. So with the Indium Phosphide PICs, you can make different types of circuits. One of the most wanted ones, or for which the Indium Phosphide PICs is more appreciated, is the possibility to have lasers on the chip. Laser is a combination it's a combination of a gain medium and filters and mirrors. In Indium Phosphide PICs, this gain medium is basically a semiconductor optical amplifier. And here, I mentioned you also need filters. In fact, these filters are optional, but these filters make it possible that you can have tunable lasers. So, we have basically different types of filters that you can use. Some of these filters are passive. They have a specific spectral response. Some of them are active, so you can apply a voltage and tune their reflection spectrum. And with that, you can make tunable lasers. So we have a diversity of filters, including gratings, like DFBs, DVRs, including Mach-Zehnder interferometers, different types, and other interferometers on chip, ring resonators, AWGs, array waveguide gratings. All these are, components that can add a specific spectral response, and with that you can build tunable filters on chip. Then we also have, mirrors that you can use the chip facets directly as a mirror. You can use gratings. You can use multimode interferometer reflectors. You can use simply loops made by waveguides to go back to your cavity. And this is a schematic just of what is the basic structure of a laser. So you have a gain medium, different types of filters that will help you to choose what is the mode, the cavity mode you want to work with in this laser cavity. And then you have two mirrors. So typically one mirror is highly reflective, so that you don't waste the power in that direction, and in the other direction the mirror will be semi-transparent, so that there is feedback to the cavity, but there is also some power going to the output of your chip. There are different types of integrated lasers. Here are some examples that have been shown in the last years, but there are certainly many more. There's a huge diversity of lasers. Here I'm showing a ring mode lock laser with saturable absorbers, also a Mach-Zehnder interferometer type of tunable laser, where you can have very wide tunability of several tens of nanometers with a good output power and so on. And here there is one wave division multiplexing transmitter, where you have several lasers in parallel, and all of them are combined with this, power combiner, array waveguide grating into a single output channel. And with this, for example, these are very useful in communications, because then you can encode the information, the ones and zeros, into the different laser wavelengths, let's say, through modulators that are in series with the lasers. So these are just some examples, but there are many more. I will also encourage you to look at the website, JePPIX, and go to the section Application Notes. It's an interesting section because you find different documents with different analysis of what is available. And I borrowed this graph from there, which basically is trying to make a comparison between demonstrated lasers, what is in blue. So a demonstrated experimental laser with certain tuning range in wavelength, going from a few nanometers to 80 or more nanometers. This is what is demonstrated, and in orange you see the application requirement, kind of an average requirement from applications in different domains. So you see that if you are looking for gas sensing, you only need basically to be able to scan the laser in a few nanometers range, and with that you can cover a spectral line. Then if you, basically for some applications, you will need a wider and wider tuning range. And the extreme will be like if you are trying to do a spectroscopy to see a specific sample on their very different wavelengths, and do imaging, like if you want to do LiDAR. Well, and with this I mean LiDAR when the approaches of people are using, let's say, the wavelength to send the beam in a different direction, so through a dispersive grating, and there you need either a very strong dispersion grating or a very wide tuning range, or both, and therefore the requirement goes to about 100 nanometers. But these are, different things that have been demonstrated, different types of lasers. You can have a look in this application note, but the summary is in this table. There are all these different types of lasers in the columns, and this is a table about performance. So you see the tuning range, the side mode suppression ratio, bandwidth and power. Tuning range can go from a few nanometers and approaching 100 nanometers. A very good side mode suppression ratio above 40 dB. Bandwidth, which varies depending on the circuit complexity and the size of the cavity, but you can really go until 100 kilohertz and even lower, much lower if you do combinations with silicon nitride chips. And power is typically several milliwatts. But if you go to the application note of JePPIX and this, you will find the different references if you want to look into the details. Gas sensing. This is one area of opportunity for PICs. And where is the gas sensing needed? Well, in chemical industry, in environmental monitoring, agriculture, monitoring pollutants, and also to be able to make respiratory warnings in different places. It still represents an opportunity because at the moment the gas sensors which can have very high sensitivity, they are really, really expensive and bulky. So they are large and very expensive, right? So with certain PICs configurations, you can actually do gas sensor, and if you can have the business case to make it in volumes, you can also go and be very cheap. So InP Photonic PICs, as other PICs, provide a small footprint, low cost. You can expect increasing performance on sensitivity in this case with newer generations of PICs that are being developed by partners. And in this specific case, Indium Phosphide, you can go, let's say, from 100, from 1500 nanometers to 1600 nanometers, and you are able to cover different absorption lines of chemicals. And with that, well, basically you can do sensing of them. And of course, it's possible to go to different other wavelengths, but that is under development. That needs specific projects and effort. But we are basically always trying to extend the range of wavelengths at which these photonic chips can work. The main technique to do gas sensing is called tunable laser diode absorption spectroscopy, which needs a laser and a photodetector, at least. And basically you have your laser, you split it into different arms. One arm is just the reference. So this is your reference laser, and the other laser, you make it pass through a gas cell where for a specific wavelength of your laser, there will be a strong absorption. So basically you do continuous tuning of your laser, and you will be able to observe, a drop in power in your monitoring photodiode, and that would mean that you are observing the presence of this gas in a certain concentration. You can retrieve information from this gas by doing this tuning and observing this absorption. So this is the fundamental technique, and there are many different configurations to do it. Going to fiber grating sensing, for the ones that are not aware, the fiber ratings are periodic modulation or refractive index in optical fibers. So basically you have an optical fiber where you have a grating embedded, which is a local modification of the material so that it has a little bit different refractive index. And with that, you can generate grating, meaning a spectral, certain spectral properties, either in transmission or in reflection, for your Bragg grating, which will change depending on the environment. So depending where the optical fiber is, when it's under certain strain, certain temperature, or others, this grating will deform and will deviate a little bit the reflection, the transmission. This is useful in different sectors like mobility, medical, energy monitoring, and others. And it can be very useful when you need basically your sensing point, the fiber, to be flexible, or with some environments which could be a little bit dangerous, where there could be chemicals. And also these fibers, of course, are insensitive to electromagnetic interferences. So if you are in such environment, it could be interesting to have this type of fibers deployed. And where the chips are, of course, where the chips generate the light, to send the light to the Bragg grating and analyze the reflected light. Here you observe some implementations. So the general principle, you can have a broadband source and you can illuminate a fiber with different fiber gratings, which are specifically reflecting one or a different wavelength. This wavelength will be reflected. So the transmission, the light that is transmitted will be lacking such wavelengths, and in your detector, in your interrogator, you can receive the different wavelengths, and then you can analyze them to observe whether whether there is a slight change in that wavelength position with respect to what you expected. That will mean that something is affecting your fiber grating, and that means external environment is having an influence. So you can do sensing of certain properties of the environment. Here there are other configurations at the bottom. This interferometric configuration, where you split, you have your laser, your tunable laser or a broadband light source, and you can split it in two arms which have the same type of Bragg gratings, both arms, but they are at a different position, right? So when this wavelength will be reflected and this one as well will reflect exactly the same wavelength, they will interfere in your detection system, and this could be much more sensitive because you are building a cavity, right? So there is a length of fiber from this to this one when you compare the two fibers, and that will make it more sensitive to small changes. Another way to make it to increase the sensitivity is also by having these FBG pairs, which is just one single fiber, but also you have Bragg gratings, but apart, you are building a cavity as well between two of the same type, and with that you can observe as well the interference effects and increase the sensitivity. And one of the partners, for example, from JePPIX, that is based in the Netherlands, is actually developing these technologies, and they have products about this. So just to mention that this is a real technology enabled by photonic chips. And now we will go to a few slides on LiDAR. The general implementation of LiDAR is, well, to have a laser source, a scanner to send the beam in different directions, and a photo detection scheme. And that's represented here in this figure, with the light source, an optical system to send the beam to an object. It gets reflected and goes back to the photosensor. And in general, you will have a timer circuit which will count the time it takes for the light to go to the object, get back, and depending on the time, you can calculate the distance at which such object is placed. That scheme will be directly time of flight, but there are other ways of doing it. Main metrics in this LiDAR sensing is field of view, how much can you cover in the angular domain, the angular resolution, so how small the beam is in the far field, and that will mean how small features you can detect. Optical power, because that will determine the maximum distance you can sense, and of course also scanning speed. There are different architectures, but the two main ones are time of flight. So like the diagram I'm showing here, so just counting the time it takes for the light to go and come back. And the other one is FMCW, frequency modulation continuous wave. Which is a coherent detection with a local oscillator, and that also helps to transcribe the velocity. That will be seen in another slide in a little bit more detail. LiDAR applications are many. The hot application will be automotive because that represents a huge market, but there are many more in topography, in energy monitoring, in manufacturing, logistics, smart cities, entertainment as well. So there are really emerging many new applications which require different things. Some of the applications will need to do sensing at a 1 meter, a few meters distance. Other applications, beyond 1 to 100 meters. Some applications only will require this measurement of the distance to the object. Other applications also need motion of the image, in other words, velocity measurements. There are for sure opportunities also to integrate LiDAR on a chip, and this is being pursued by several startups and research labs. And the idea is to be able to make the whole LiDAR system smaller, so miniaturization, that with a PIC you can also have a reliable operation, that you can do scanning with a solid state optical phase array. So there are no moving parts as in traditional LiDAR systems, which have mechanical components that deflect to change the direction of the beam, or have rotating mirrors. So in this case, you can achieve it with purely solid state means. There is also a trend to go to high temperature operation because certain environments will require that from LiDAR components. You can expect also energy efficiency by doing it in indium phosphide. That means you can work in an high safety regime as compared to other wavelengths available, let's say. And there's also potential for low cost at high volumes. LiDAR on chip, there are many flavors. Many things are being done. Some of the highlights, I would say, is to try to integrate indium phosphide with silicon to bring the indium phosphide, the lasers together with the grating couplers and do optical phase arrays to try to implement the coherent detection on a single chip, to do large-scale integration, and that will be to increase the performance of the beam forming, so achieving a higher resolution of the image. And that has been tried with silicon photonics, but also with indium phosphide photonic chips. And currently there are a number of trends in this field to integrate optical amplification on chip in these LiDAR chips, to integrate frequency modulated continuous wave lasers, to have full on-chip coherent detection, and also to integrate the chips with additional lenses, optical elements that help to do beam shaping according to the different applications out there. I will talk about two components, optical phase arrays and lasers for LiDAR. So with Indium Phosphide, it's possible to do optical phase arrays that have amplitude and phase control. That's quite important, and I would like to underline the amplitude control. So that means integrating semiconductor optical amplifiers is possible in this platform. And then, of course, the challenges are to go to a large number of emitters so that you can achieve a high angular resolution. And this amplitude control could help you in, enabling efficient operation or range flexibility. And this optical phase array is basically an array of antennas in which you can tune the phase independently from every antenna. And by doing that, you can calibrate the whole array such that the radiation pattern will be pointing in a specific direction. So there is constructive interference in a certain direction and destructive interference in the rest of the field of view. And well, that is possible. As an example, we have demonstrated these optical phase arrays in Indium Phosphide, as I mentioned. So here I present an example of an 8-channel OPA, and this will be the near field, basically at the output of the different antennas. This will be the calibrated far field response, where you are, after you have to calibrate all the phases of the channels in order to produce constructive interference into a specific direction. And we have demonstrated that this type of chips can have a very broadband response, so you can operate them into a very wide wavelength range with a single calibration dataset. And that's quite important if you want to integrate it with tunable lasers. As I mentioned, also optical amplification is possible, and work has been done, it's just not published. That's why I cannot show it here. I mentioned FMCW, so frequency modulation continuous wave. This offers advantages over time of flight because you can measure not only the distance but also the velocity of the objects through the Doppler effect. Then it provides also a high sensitivity because it's based on coherent detection, and that enables long reach sensing and low power operation of your components, which of course helps for the eye safety, concerns. It's a coherent detection, so there is a strong immunity to interference. And one disadvantage is that it has a higher complexity than time of flight, right? So there's a schematic here how this works. So basically you have an emitter, your laser, where you are modulating the frequency of it. So it's not working at a single frequency. You are moving up and down in a linear way your frequency. So this is time, this is frequency. So you are modulating, going up, down, which is also known like it's also known as chirping the laser. And you send that chirp laser to the object, and you receive it as well. And at the detector, you produce a beating note between the received signal and a local oscillator, so a portion of your original laser. And based on that, you will receive this. You will have this beating frequency between the received signal and the local oscillator. And with that, you can retrieve the distance and the velocity of the object. Lasers with FMCW modulation have been also demonstrated. So in this slide, I show a laser that has a relatively wide tuning range. So it can be operated from 1512 to 1563 nanometers in this case. Also a nice SMSR. Milliwatt output power. And you have we have tried them on their frequency modulation, and we have shown that it's actually possible to modulate this laser in the full wavelength range. And more importantly, that can be actually done very linearly. So we have achieved very linear modulation. That is, it's important not to compromise the resolution of the retrieve position of the object. And using those type of lasers, well, here you see in orange basically is the voltage signal applied to the modulation, to the laser to modulate it, and in blue you will see the frequency being chirped. Yeah, so you don't observe, but it's basically the frequency is increasing, or well, increase in this case decreasing or increasing, and that's what you observe here. So the instantaneous frequency goes down, goes up, goes down. Basically, it's a triangular signal. And with that, we have shown using, for example, this type of experimental setup, the suitability for performing LiDAR sensing. In this case, the light does not go to free space to determine the distance to the object, but we understand and characterize the feasibility of this laser for LiDAR by doing it in the fiber. So basically, instead of letting the light go to 2 meters, to an object that is placed at 2 meters or 1 meter far and then coming back and having a delay of 2 meters, we introduce that delay directly in the fiber. And then we do the coherent detection. And with that, you can observe this beating node, which is at a specific frequency. And that frequency can be correlated directly to the position of the object, or in this case, to the delay introduced by the fiber. So we have achieved a frequency excursion of a few gigahertz, depending on the laser, a very high linearity, and that enables the range resolution of 10 to 20 centimeters. And that's all from my side. You are welcome to get in touch with JePPIX coordinator. There are a few social media channels here where you can see news, opportunities to collaborate, and so on.